The backpropagation algorithm. Backpropagation algorithm is probably the most fundamental building block in a neural network. It was first introduced in the year 1960s, and almost 30 years later, that is, in 1989, it is popularized by Rumelhart, Hinton, and Williams in a paper called Learning Representations by Backpropagating Errors. The algorithm is used to effectively train a neural network through a method called chain rule. In simple terms, after each forward pass through a network, backpropagation performs a backward pass while adjusting the model's parameters, that is, weights and biases. Backpropagation is an important mathematical tool for improving the accuracy of predictions in machine learning. Essentially, backpropagation is an algorithm used to calculate derivatives quickly. Artificial neural networks use backpropagation as a learning algorithm to compute a gradient descent with respect to weights. Desired outputs are compared to achieved system outputs, and then the systems are tuned by adjusting connection weights to narrow the difference between the two as much as possible. The algorithm gets its name because the weights are updated backwards from output towards input. The backpropagation algorithm learns the weights for multilayer network. Given a network with a fixed set of units and interconnections, it employs gradient descent to attempt to minimize the squared error between the network output values and the target values for these outputs. In backpropagation algorithm, we consider networks with multiple output units rather than single units as before. So we redefine the error capital E to sum the errors over all of the network output units. Capital E of weight vector W is equal to 1 by 2 into summation of for all small d belonging to capital D and for all small k belonging to outputs TKD minus OKD the whole square. Here small d represents each and every input in input space capital D. Similarly, small k represents each and every output belonging to the output space. Outputs is the set of output units in the network. TKD and OKD are the target and output values associated with the kth output units. Small d represents training example. The backpropagation algorithm is stated as shown. Each training example is a pair of the form x, t vector, where x vector is the vector of network input values and t vector is the vector of target network output values. Neta is the learning rate. For example, 0.05. Ni is the number of network inputs. N hidden is the number of units in the hidden layer and N out the number of output units. The input from unit I into unit J is denoted as x of Ji, and the weight from unit I to unit J is denoted as Wji. Create a feed-forward network with Ni inputs and N hidden units and N out output units. Initialize all network weights with small random numbers. Until the termination condition is met, do the following. For each x, t in the training example, do the following. Propagate the input forward through the network. Input the instance x to the network and compute the output OU of every unit U in the network. Propagate the errors backward through the network. For each network output unit K, calculate its error term delta K. Delta K is equal to output at kth neuron multiplied by 1 minus output at kth neuron multiplied by target at kth neuron minus output at kth neuron. This we call as equation 10. For each hidden unit h, calculate the error term delta h. Delta h is equal to output at hidden neuron multiplied by 1 minus output at hidden neuron multiplied by summation of k belonging to all the outputs, that is, for each output belonging to output space of wh of k into delta k. Update each network weight wji as wji is equal to old value of wji plus delta wji, where delta wji is equal to neta into delta j multiplied by x of ij. Derivation of the backpropagation rule. Deriving the stochastic gradient descent rule. Stochastic gradient descent involves iterating through the training examples one at a time. For each training example D, descending the gradient of the error ED with respect to this single example. For each training example D, every weight wji is updated by adding to it delta wji. Delta wji is equal to minus neta of derivative of total error ed with respect to wji. We will call this equation as 1, where ed is the error on training example D summed over all the output units in the network. ED of W is equal to 1 by 2 summation of for all k belonging to the output. That is, we will consider all the outputs in the output space. T of k minus O of k, the whole square. Here, outputs is the set of output units in the network. T of k is the target value of unit k for training example D, and O of k is the output of unit k given training example D. The derivation of the stochastic gradient descent rule is conceptually straightforward, but requires keeping track of a number of subscripts and variables. Those are x of ji is equal to the ith input to j. Wji means the weight associated with ith input to unit j. Net of j means summation of wji into xji. It is the weighted sum of inputs for unit j. O of j is the output computed by unit j. T of j is the target output for unit j. Sigma is the sigmoid function. Outputs means the set of units in the final layer of network. Downstream of j means the set of units whose immediate inputs include the output of unit j. We will derive an expression for delta E to the delta W, that is, the total error derivative with respect to weight ji in order to implement the stochastic gradient descent rule. Seen in equation, delta wji is equal to minus neta of delta ed upon delta wji. Notice that the weight wji can influence the rest of the network only through net j. To solve this, we will use the chain rule, that is, derivative of ed with respect to net j multiplied by derivative of net j with respect to weight wji. Here, derivative of net j with respect to weight wji is nothing but xji, because xji into wji will give us net ji. Hence, derivative of net j with respect to wji is substituted as xji. Derive a convenient expression for derivative of total error with respect to net j. For this, consider two cases in turn. The case where the unit j is an output unit for the network, and the case where j is an internal unit, that is, hidden unit, where k is the network output unit. We will take these two cases one by one. Consider the first case where training rule for output unit weights. wji can influence the rest of the network only through net j, that is, weight will influence the rest of the network through the net input. Net J can influence the network only through OJ, that is output. Therefore, we can invoke the chain rule again. We need to understand that weight is related to net input. Net input will influence the output. Hence, the chain rule is invoked. Delta ED with respect to delta net J, that is derivative of total error with respect to net J, is equal to derivative of error with respect to output, that is OJ, multiplied by derivative of OJ with respect to net J. To begin, consider just the first term in the equation number 3, that is derivative of error with respect to OJ is equal to derivative of half of summation of for all k belonging to output space T of k minus O of k the whole square. This we need to differentiate with respect to OJ. The derivative delta tk minus ok whole square with respect to OJ will be 0 for all output units k except when k is equal to j. We therefore drop the summation over output units and simply set k is equal to j. Our equation will look like the one shown, that is derivative of error with respect to OJ is equal to derivative of half of Tj minus Oj whole square with respect to Oj. This, when we differentiate, we will get minus of Tj minus Oj. Next, consider the second term in equation number 3. Since Oj is equal to sigma net j, the derivative Oj with respect to net j is just the derivative of the sigmoid function, which we have already noted is equal to sigma of net j multiplied by 1 minus sigma net j. Therefore, our equation turns out to be delta Oj with respect to net j is equal to delta of sigma of net j with respect to net j. This equation will result in Oj multiplied by 1 minus Oj. Substituting the expressions 4 and 5 in equation 3, we will get derivative of total error E with respect to net j is equal to minus of Tj minus Oj multiplied by Oj into 1 minus OJ, and combining this with equation 1 and 2, we have the stochastic gradient descent rule for output units. Delta Wji is equal to minus neta of derivative of error ED with respect to Wji is equal to neta of Tj minus Oj multiplied by Oj into 1 minus Oj multiplied by Xji. We will now consider the second case, training rule for hidden unit weights. In the case where J is an internal or hidden unit in the network, the derivation of the training rule for Wji must take into account the indirect ways in which weight Wji can influence the network outputs and hence error ED. For this reason, we will find it is useful to refer to the set of all units immediately downstream of unit J in the network and denoted this set of units by downstream J. Net J can influence the network outputs only through the unit in downstream J. Therefore, we can write derivative of ED with respect to net J is equal to summation of for all K belonging to downstream J, derivative of ED with respect to net K multiplied by net K with respect to net J. Again, chain rule is used here. This turned out to be summation of K belonging to downstream J minus delta K into net K with respect to net J. This is equal to, again we will substitute net K with respect to net J as chain rule. So our equation will be for all K belonging to downstream summation of minus delta K multiplied by derivative of net K with respect to Oj multiplied by derivative of Oj with respect to net J. This turned out to be minus delta K into Wkj into derivative of Oj with respect to net J, because we know that weight into output is equal to net input, that is equal to summation of K belonging to downstream J delta K multiplied by weight Kj into Oj multiplied by 1 minus Oj. This we call as equation 8. Rearranging the terms and using delta J to denote minus ED with respect to delta net J, we have delta J is equal to OJ multiplied by 1 minus OJ into summation of for all K belonging to downstream J delta K into WKJ, and delta WJI is equal to neta of delta J multiplied by XJI